Len, it's good to see you. I remember our last conversation in the basement on scientific breakthroughs. It was good fun. I think we had previously done an interview at Caltech years ago.
Yeah, those are both fun, and this is now the COVID version.
Yeah, well, we're
These beautiful spaces here.
Yeah, well, we're this is the real world now. When we see each other in person, it's a different world. We're going to wait for a few seconds to get other people online, and then we can start. But I should tell you that our series on scientific breakthroughs that you and many others participate will be broadcast premiere on PBS the next couple of months or so. We're a little delayed because of COVID and the difficulty of post production. But we're very excited about those shows. I think they're very significant.
We're looking forward to it.
Yeah. And you've been very prolific and many books, and we're excited to talk about it. And today should be great fun. So we're going to make a kind of a formal introduction. People have now joining us, so let me go ahead and do that. So hello, everyone. Welcome to Closer to Truth Live. Thank you for becoming Closer to Truth members. Today's conversation is the first in a series that will be available exclusively to members. And I'm very pleased to be joined today by a Closer to Truth long-term contributor and good friend, Leonard Mlodinow, whose new book is just a terrific read, Stephen Hawking, a Memoir of Friendship and Physics. It has been my personal companion for the last week or so, and it's been a great joy to go through. The book is available now in hardcover, but it will be released in paperback on May 18th. So all Closer to Truth members, go and get it. And if you have questions for Len, send them in. We'll be dealing with that later. But the book was really terrific. And I see it, there are three aspects to it, and it's all woven together. Certainly the physics, as Stephen Hawking had developed, categorizes some of the most important areas in cosmology and universal origins, and we'll get into all of that in great detail. But the clarity with which Len presents it is really terrific. Second, obviously, is Stephen's remarkable personal story, and we all know the superficiality of it and what we've seen in the media. But to have Len's first person description of what it really was to me startling, as much as I thought I knew. And then the third part is really Len's own first personal experiences and reflections, and he's very candid. He talks about his own frustrations and dealings, and it really works well. So Len, let's start. You begin the book at Stephen's funeral, and as the casket passes by, even though you, as Stephen, did not and do not believe in an afterlife, you said you sent Stephen your best wishes for the eternal future. What did you mean by that?
Well, of course, intellectually, well, I shouldn't say of course, but intellectually, I don't believe in an afterlife or God or eternal spirit. I don't see any evidence for that. But I think the reason that we have religion and that a lot of people do believe that is that in a human being, there's certain unconscious intuitive feelings. And I was feeling that at the time, that even though I knew that he was gone and it was just his physical shell that was passing me, I kind of felt something funny, like there he was right there, and that he would be going to his resting place forever. And I don't know, I felt like kind of a connection at that point. So I just wrote what I felt. I can't explain it, and I'm not saying that I'm not saying that I believe that there was anything mystical behind it, but it's just how I felt as he was passing.
You make the comment that Stephen was a spiritual man. Obviously, that's not in a traditional spiritual sense, but how so?
Well, there's different ways of looking at the word spiritual, but there's also it's not just the supernatural spirits. There's the human spirit, and Stephen was very spiritual in the sense that he he was very focused on the human spirit, on his own life, on the people around him, what they were thinking, what they were feeling, how he could interact with them, what life was about, where we were, what we were all doing this for, where we all came from. I mean, he was asking the same questions that religious people ask. Why are we here? Where do we come from? What is this all about? What is our place in the universe? So I consider that spiritual. It's just that he didn't believe in biblical God.
You make the comment that that there was something in Stephen's thinking, not in terms of an immortal soul as traditional religion, but something that distinguishes humans from animals. And the word soul was used. Is that a kind of a metaphor, or is there something substantive behind that thinking?
Well, I think there's something substantive behind it, but I wouldn't say it's literal either. I think what he believed was that human beings on Earth have a certain special brain, a brain that's different from that of other animals. Of course, we don't really understand how other animals think and feel, but it seemed that our ability to understand who we are and that we even exist is something special. And so that's the kind of soul of the person, meaning the essence or the psychological essence of the person, not meaning a spirit that exists outside of the body. He did not for a minute believe in that.
When did you first meet Stephen?
Well, actually, I first met Stephen, it must have been 78 or something like that. I went to a talk at Princeton to see him, but that was just a very brief, and I'm quite sure he did remember me. I was just a student back then, but I really met him for the purposes of our later relationship. Shortly after he contacted me about writing together, that was 2003, I believe. So he had seen my book, Feynman's Rainbow, which was about my finding myself really in life, but through a relationship with the iconic physicist, Richard Feynman. And then Euclid's Window, my first book about curved space. And at the time, he was interested in finding somebody to write with, and he wanted someone who I think wrote with a certain sense of humor and but understood physics. And he liked those books, so he contacted my agent, Susan Ginsburg, who I'll give a shout out to because I know she's watching. And so one day I get a call, and she says, "Hey, I don't know if this is going to happen or not, but just in case, I'm wondering if it was going to happen, would you possibly be interested in writing a book with Stephen Hawking?" And I said, "Well, I got to think about that." "Yes, I'll do it." And that became A Briefer History of Time, which I think came out in 2005. And what he was looking for at that time was somebody to help him rewrite A Brief History of Time, because he, as he felt, that a lot of people bought it and very few people read it, and almost nobody understood it. And even his good friend Kip Thorne, Nobel Prize winning physicist now, he told me he didn't understand it either. So I helped Stephen with that, and we wrote A Briefer History of Time, which really should have been titled A Clearer History of Time, but we thought that wouldn't be good, so we tried to find some kind of title for it. And that book was pretty easy to write because I had the material in front of me, the Brief History of Time. It was just a matter of looking at what I should cut, add, what required further explanation, and so on, massaging it, reorganization to make it clearer. And we did most of that by email, but I was on the faculty at Caltech at the time, and so he would come once a year. He had done this for decades, to Caltech for several weeks, maybe a month. And we would meet there and otherwise email each other. And after that book came out, I had this idea that Stephen had been basically writing the same stuff for decades about his work in the 70s and 80s. That's what A Brief History, and of course, Briefer History was, and Universe in a Nutshell. And he has done some pretty exciting work in the 2000s. So this was by now around 2004. 2005 that I started talking to him, and I had this idea, well, let me see if he wants to write a book about his current thinking and his recent work. And so the next time he was at Caltech, I went out into his office, and I proposed it to him, and I thought he would go away and say, let me think about it. But he did the same as me. He went, yeah, let's do it. Of course, that was the last easy thing about that book. But he agreed, and we just started on it right there.
Yeah, that's great, and we'll get into it in detail. You know, I was reflecting that many times when famous people write books, they have ghostwriters whose name does not appear. They're paid well and they're happy, but their name doesn't appear. But you're very prominent in these books, virtually, not literally, a co-author. Did that conversation ever occur where the question is whether you'd be a ghost or
No, he never suggested that, and I wouldn't have done it. I may have my own successful career writing, and I didn't need to be or want to be a ghostwriter for him. He asked me. Well, the first book says with, and that's I think appropriate because, as I said, it was a rewrite of a brief history.
Sure.
The second book is and because we did it together, but so they never proposed that, and nor did he even want that. He did not want to go. If you read my memoir, you'll see that he did not want a ghostwriter. He was. We wrestled over every word in the book, so he wanted someone to help him with it, to work with him on it, make perhaps the burden easier. But actually, the way the second book came up, it wasn't even that, right? It was like I had this idea to write the book, and I said, do you want to write it? The first book, he wanted someone, some help, but kind of a partner to help him with it. The second book, from the start, was really a co-authorship because I came to him with the idea, and he wanted to do it, and he certainly didn't want to give me free rein and then just put his name on it. It was
that brings up the opposite claim that's opposite from Ghostwriter, and that is the assumption that is because of Stephen's terrible handicaps, which he remarkably overcame in unique ways. But the assumption is that you did all the writing and that he might have given an idea here and there and using his name, but basically it's all your writing. I know that's not the case, but why don't you explain how that happened?
How
in fact Stephen was really involved.
Anyone who knows Stephen,
the assumption is that you wrote the book and he put his name on it.
Yeah, right, which is somewhat the ghostwriter, except I have my name on it. But no, not at all. Well, I can't. As I say, I came to him with the idea, and Stephen is, anyone who knows him, and if you read my book, you'll get to know him. He is the opposite of the type who would do that. I mean,
No, it's the opposite question. The assumption is that you wrote the whole book.
That's what I mean. He would not ever let me write the whole thing and put his name on it. I could not write a sentence without putting his name. The way we worked on the book was we first debated for about a year what would be in the book. We wrote a very detailed outline, which we, followed to some, I would say 75% followed. We wrote a very detailed outline, and then we divided up not chapters but sections. So each chapter we would give a section. You do this, I do that. We would each choose sections to write, and then he would write his sections and email them to me. I would write my sections and email them to him, and then we would have long discussions when he came to Caltech, and also I would go several times a year to Cambridge. So that's how it worked. But in the end, it went back and forth so much that you couldn't really identify, in most cases, what was his words or what were mine. And he certainly, the last thing that he would ever do is let me write something in his name. He made sure that every word was not, I may have written words, but if he didn't like the word, we debated it, we changed it. It was, he was so detail oriented that there was nothing in there that was purely mine. And so if we had a disagreement on something, we would argue it out. Of course, he would usually win. And that's how it worked.
How long was it from when you presented the idea to when it was published? How many years?
I think it was 5 years. It was about a year, as I said, working out the outline, and then I think when we had that, we sent it to the publisher, and then about 4 years to write the book. And there's a nice story in the book about how that. It was supposed to be, I think, a year and a half to write the book, and then it was supposed to be 2 years, and then it was supposed to be almost 3 years, and so on. And because he was so slow sometimes, or so detail oriented, and there was so much to go over, and he had such a a lot of other things to do, and it takes him a long time to be able to do things. That he didn't really care
It's a
when we
remark.
got it done, and he kept blithely just saying, "Well, we're not going to get it done. Who cares about the deadline?" So,
Yeah, the deadline is one of the leitmotifs of the book. You keep seeing it over and over again. Really a remarkable story to see the whole process through your writing the book. So highly recommended to everyone. Stephen Hawking, a memoir of friendship and physics. So let's start now with the physics, because that's what Closer to Truth is about. It's a wonderful story to hear. But so we've got to do it briefly, but let's go through each of the key areas of Stephen's physics as it begins to appear in both books, A Briefer History of Time and now, and then in the Grand Design. So describe briefly Stephen's first discovery, the mathematics, I think it was his thesis, his doctoral thesis, proving the Big Bang is a necessity of Einstein's equations.
well, Stephen was a graduate student in the 60s, and he was about 3/4 of the way through his PhD thesis and hadn't come up with anything particularly interesting. And then his office mate went to a talk by Roger Penrose. Stephen was too ill to go to the talk, but when he came back, he told Stephen about it, and then Stephen got this idea, which turned out to be his first big contribution. It was, in a way, very serendipitous that his roommate would go to the talk and would tell him about it, and Stephen started thinking in his usual way, kind of turning the idea upside down. What Penrose had done, and he just got the Nobel Prize for this, was Penrose had shown that Einstein's equations lead to black holes. People knew for decades that under certain circumstances, Einstein's equations would lead to black holes. The theory of general relativity and the non-quantum theory of gravity. People knew that would lead to black holes if you started out with a huge mass that was spherically symmetric. So if you made that mathematical assumption, people could solve the problem and see that it would collapse into a black hole. But real life isn't like that, and the stars that collapse into black holes are not spherically symmetric. There's parts that are more dense, less dense. It's constantly dynamic. Things are moving around. It's a storm of hot gases, and so that theorem didn't really apply to real life. And what Penrose did was work out some mathematical techniques whereby he could prove that a real star of a certain size would collapse into a black hole. So that's what he just won the Nobel Prize for. And Stephen saw that, and in his usual way of thinking, which was very creative and unusual, he always found different angles for things. And he asked the question, could we reverse this and show that the universe could have started as a kind of analogy in a state that's analogous to a black hole, and then reversing it exploded, or I don't like the word exploded, but expanded into the universe. So he used Penrose's technique, but reversed the logic, and he showed that Einstein's equations show that the universe started from a Big Bang. So that was a very big contribution. He didn't totally finish that work. He ended up working on it with Penrose for a few years, but he finished his PhD in '66, and that was the fourth chapter of his PhD thesis. And the other three you could just toss, but that one was not only enough for a PhD, but enough to make him famous in the cosmology community. And one thing I want to add is that at the time, one of the remarkable things about Stephen's career was that he just followed his own nose, and it took him to good places. And at the time in the '60s, cosmology and the whole idea of black holes and Big Bang was not very popular amongst physicists. It was kind of looked at as a dead end. People thought that we would never be able to observe anything about the early universe, at least before 1964 they did. And then the microwave background was discovered, and it took a few years to understand it. But Because of that, and because there were no black holes around and we didn't think we'd observe any, of course we have now done that, but back then it didn't seem that this field was very connected to observation. It seemed almost like religion or philosophy. And so, as Richard Feynman famously said, he said most of the people in the field were dopes. I won't comment on that, but there wasn't a lot of interest in the field, and Stephen didn't really care. So one of the interesting things was he got interested in this himself. He was interested in these big questions of where we came from and where the universe came from, and so he went into that despite everyone else's disinterest. And because of people like him and also Penrose, it became a very hot, exciting field, and now is considered one of the most exciting fields in physics and in the
black holes become
popular world. I mean, popular science world, people are also very interested in it.
Black
Nobody had heard of it back then.
Black holes are like a laboratory of physics. You can't do experiments in cosmology, but you can do theoretical assessments and experiments with black holes. So black holes is the ultimate test of general relativity and quantum mechanics and their interaction, and has been this fertile laboratory to enable tremendous advances. So let's talk about Stephen's now relationship with black holes, and give me, we've got to do it pretty quickly. We have a lot of Stephen's cosmology to get to. We don't have a lot of time, so make it quick. But integrate Hawking horizon of the black hole horizon, Hawking radiation, which is perhaps his most famous thing, where black holes can radiate and ultimately evaporate and explode, and then the information paradox. So all black hole, interesting. I'll give you 10 seconds, well, maybe a little bit more, to deal with all of those.
All right. Well, the answer is, what is it? 48. The Douglas Adams answer. So one thing that Stephen, and this is kind of technical, so I will do this in 10 seconds, is he created a new vision or a new definition of the black hole horizon. The horizon is a place in space. Originally it was a place in space, but now it's a region of space-time outside of which nothing can escape the black hole. So before Stephen, people defined that horizon at a given time, and they defined it in space. And he realized that because that was what we call non-relativistically invariant, that's different for different observers, that wasn't the best way to do it. And he found a way, mixing space and time, to do it. It's kind of a technical thing, but it is in the book. So there you go. But his next big work that people may have heard about was to apply general relativity now to black holes. So his first work was to take Penrose's application of general relativity to black holes and apply it to the universe and come up with the Big Bang, or to show evidence for the Big Bang theoretically. But his second, that one he did after that, was he turned to look at black holes and what general relativity says about that. And with two other guys, Bardeen and Carter, he came up with these things called, with a set of laws called the laws of black hole mechanics. So those were, what they studied was what are the properties of black holes according to Einstein's theory. And I can go into them if you want, but one of the interesting ones was that, of course, that a black hole always expands. It takes in matter, and that the event horizon, or the surface, so to speak, of a black hole never shrinks because it's always sucking stuff in and nothing can get out. That makes a lot of sense. And so there are a few laws like that. And that was, you might say, his second or third major contribution. Now, somebody named Jakob Bekenstein, who was a graduate student at Princeton at the time, looked at those laws and recognized a parallel, which other people had noticed also, but he took this parallel very seriously between those laws of black hole mechanics and some other laws in physics that we call the laws of thermodynamics. And Bekenstein believed that you should take those, the laws seriously, like the analogy seriously. And so therefore that black holes would have something called entropy. So I don't have the time apparently to get into what that is, but entropy is a measure of disorder, and black holes were thought to be something very simple that couldn't really have any disorder because they have very few properties. They're not made of anything. They're just there. They're like an elementary particle. An electron is a point particle. It has a mass, it has a charge, a spin, but it doesn't have internal structure. So it doesn't make sense to talk about disorder inside it because there's no internal structure. And a black hole is similar. It has mass, that's a fundamental quality. It can also have charge and spin, which we don't need to talk about today. Those are just a technical thing, but essentially it's just a featureless thing that has this one property. There's no inside to rearrange and to make and put in order or to mess up or to make chaotic. It's just there's nothing inside it, so there doesn't have any states to be disordered, and so that it doesn't have entropy. Entropy is supposed to be zero. Bekenstein didn't believe that. Hawking didn't like what Bekenstein said and ridiculed him, and most people did, because if the laws of physics say that if a black hole has entropy, then it has a temperature and it should be radiating energy away. And if it's radiating energy away, it's going to be shrinking, and then it's not a black hole anymore. So people didn't believe Bekenstein. And then Stephen happened to be in Russia to see a friend and famous physicist named Zeldovich. And Zeldovich brought Stephen a calculation he had done, which showed that if a black hole is spinning, it radiates energy away. Now, that's not a revolutionary thing, because that energy doesn't have to come from shrinking the black hole. It doesn't have to come from the mass of the black hole leaving. It could come from the spin slowing down. So that wasn't revolutionary, but it was very interesting. And Stephen didn't believe Zeldovich's calculation. This is a theme that I talk about a lot in the book, which is that we can't solve the equations in physics. Everything is made by approximations and throwing away certain things, arguing that they're not important, focusing on other things, doing mathematical approximations. And Stephen's work was often questioned on that basis as well. But here Stephen was questioning Zeldovich, and he said, I'm going to go home and just calculate it myself, my own way. So he sat down to do that, and that's how he discovered that not only do spinning black holes radiate, but black holes that we call quiescent, that are not spinning or changing, they're just sitting there, also radiate. And that was his big breakthrough. And it illustrates another interesting point about Stephen, was that he was not afraid or did not hesitate to prove himself wrong. Most people in physics will, especially if they get famous for something like Hawking's laws of black hole mechanics, they're very, takes a long time to get them to let go of it when someone else shows it that it's wrong. But in this case, Stephen let go of, he himself showed that they were wrong, and he let go of those laws. And after, maybe right away, but after a few months, convinced himself that he was wrong before. And it's interesting to understand what wrong in what way. He wasn't that his work before was wrong, but his work that he had done on laws of black hole mechanics just a couple of years earlier, that was based only on general relativity, Einstein's theory of gravity. But now, in trying to reproduce Zeldovich's work, he realized you had to mix quantum theory in. So it's not that he had done wrong calculations, but he realized they were wrong to ignore quantum theory. And when you put quantum theory in, you get this evaporation, that the black hole actually radiates energy, loses mass, shrinks, and eventually disappears. That was extremely controversial for the same reasons that people didn't like when Bekenstein said it. And let me just very briefly tell you why. The reason is that in physics, in quantum theory, information is preserved. So if you have an atom, let's say it's a helium atom, and it has certain information that makes it a helium atom, that it's made of quarks, for example, and electrons. It has an identity. That's a piece of information about it. And according to the laws of quantum theory, whether you're going backwards or forwards in time, the information is never destroyed. But in a black hole, if I take a helium atom and throw it in the black hole, and I said, also take some hydrogen, say a couple of hydrogen atoms and an electron or whatever, throw them in the amount that weighs the same amount as the helium atom, and throw that in the black hole, well, we've lost the identity. All we have now is a black hole that's slightly heavier. No record of what it is that made it up, what fell in. Now, if the black hole is surrounded by an event horizon and cannot communicate with the outer universe, well, that's not such a big deal. But if we throw something in, so let's say you, Robert, we throw you into a black hole, and then the black hole radiates away and eventually disappears, and no Robert comes out, or we don't know that, or Robert or his remnants come out, no identifiable pieces that we know came from a Robert come out, then we've lost the information that Robert ever existed. Once you fell into a black hole, and people after the black hole disappears start looking for where is this particle called Robert, they don't know that you ever existed. So that is a contradiction of quantum theory, and that's why people really were excited and or upset by his discovery of Hawking radiation.
Stephen is very famous for making bets, losing bets, and being very happy to lose bets.
Right, and so so he made a bet with a famous bet with Kip Thorne and John Preskill, two other Caltech faculty members, and he and Kip bet that this the information actually is lost and quantum theory is wrong, and John Preskill bet the other side. And in the 90s, I talk about that in the book, Stephen comes up with a theory that he actually was wrong about that bet, not that black hole evaporation is wrong, but that the information is lost forever is wrong. And I won't go into the calculation, but he found a way of calculating and examining this. He thought he found where the information went when the black hole shrunk. So he gave a lecture on that, conceding to Preskill, and Preskill accepted the concession, but said he didn't believe the calculation because it wasn't. He had to study it more, and it wasn't detailed enough. And Kip refused to concede because he agreed with John that it wasn't good enough. And Stephen admitted that he never finished the calculation. He got to a certain point in the calculation. It was a very difficult calculation. Then he did what he often would do, is give it to a graduate student to finish. And this guy wasn't up to it and never finished it. So the calculation never did get done. And people just kind of, no one really, people say, okay, that's a possibility, but nobody really accepted it. And people are still working on that problem to this day. But it's really interesting because it shows, number one, that physics is about waving your hands, and it's just not the exact science, even theoretical, that people think it is. And it also, again, illustrates how Stephen flips himself if he finds that he was wrong. And it also illustrates another important thing about Stephen, which was that in the early 70s, when his illness started to really take over his body, he made a very important decision in his life, in his physics life. And that was to be not so rigorous. So what we call rigorous is, where are you in that spectrum between you're a mathematician and everything has to be proved and you therefore make no progress, and you're very sloppy, and not only do you not say everything has to be proved, but people don't even believe what you say. And Stephen used to be, where Roger Penrose is near that far end of being very mathematical and proving things. But then he really realized that he has to be more to the other end. And he told Kip told me this, that he realized he could either be right, or that he could either be rigorous or discover things. And he decided to discover things and take that chance that he's not necessarily proven.
But let's now go to the next big topic, which is more controversial in the category of discovering things and uncertain, and that's the origin of the universe. And there are several big ideas that Stephen had that you've developed in your book and showed the process. So describe, first of all, the no boundary proposal.
So that's something, the no boundary proposal is a work that Stephen did with Jim Hartle up at UC Santa Barbara. And if you look at his evolution, Stephen, as I said, first applied Einstein's theory to the origin of the universe and to black holes. And then he added quantum theory to that and worked on black holes. Well, for in the early 80s, he and Jim Hartle added quantum theory to the theory of the origin of the universe. So that was no longer just Einstein's theory, but they wanted to know what happens when you apply quantum theory to it. And so they investigated that question and found some very interesting, created a very interesting theory. And the key to the theory is that something that's really very intuitive, which is when you go, which is that gravity which is that the effects of gravity on space and time in the early universe were stronger and stronger the earlier you get. If you imagine the universe today having a certain observable universe having a certain size, and you go back in time, that will be smaller and smaller and smaller. And what that means is that all the matter and energy, since matter and energy is never destroyed, it can be converted into different forms, but it's never lost. That the density, the amount of matter energy per unit volume in the earlier and earlier universe is greater and greater. So the further back you go, the more mass you have concentrated. Well, Einstein's theory tells you that, Einstein's classical theory of general relativity tells you that when matter is concentrated, or when you have a very strong density of matter, a very strong gravitational field, it affects space and time, and they start to get warped. And what Stephen realizes is that if you go back far enough in time, the question of going backwards in time starts to lose its meaning, because time starts to look just like another direction of space. So things got warped so much that time is effectively like another dimension of space. The analogy that Stephen liked to use was of if you look at the older way of thinking, that time was like a railroad track, linear, and you could go back as far as you want it, and there must be some beginning. But in Stephen's idea was that it's more like a sphere, and if you're on somewhere on a sphere and you start moving, let's say south, you're going further and further south, but you never reach an end, you never reach a boundary, you just go past and you just keep going. So everything's smoothed out if you look at it that way. And so in the no boundary proposal, applying quantum theory to that, they realized that there really was no beginning of time, and no beginning of the universe, and that the actual Big Bang, the idea of that the Big Bang happened at, let's say, t equals 0, and everything began, is not right. That at some point you have to stop tracing things back, and the picture looks much different.
So the second piece is the quantum universe idea, taking Schrodinger's equation of the wave function that are normally applied to individual particles, and expanding that, not just to molecules and macroscopic objects, but applying it to the entire universe, such that there is, if I get this right, that at the initial moments, I don't want to use the word time, that the initial state, there's the superposition of all different universal histories, such that, if I get this right, the present helps determine the past in sort of a top-down approach, that there are all these universal possibilities, universal history possibilities at some point, at some moment in the past, and that where we are today, in essence, helps select out of that infinite number of possibilities that which actually occurred.
Yeah, that's right. So when he did the no boundary proposal, Stephen was working with something called the wave function of the universe. So the idea is that just like particles, like electrons, have a wave function to describe them, the universe should have a wave function. Now, in the 2000s, this is the work that I was finding so interesting, and I was reading about in the early 2000s. He started working on something called the top-down cosmology. And that's related to the work, to the no boundary proposal. What he realized is that if you're really treating the universe as a quantum system, then the universe has many histories, because quantum systems don't have just one history. They have many parallel histories, and the wave function describes what the probabilities are of each history, so to speak, in a hand-waving way. So he realized that you have to, if you're treating the universe as a quantum system, you have to allow for, so to speak, the quantum fluctuations of the history of the universe. So it's not just the quantum fluctuation of where's the electron, but what is the character of the universe, and that is not definite at any given time, because in quantum theory, stuff isn't definite. Now, but one of the big points in that theory was that the early universe, since there were nobody there making measurements on it, that the early universe was in a superposition of different states. It wasn't just in a specific state. And today it's also in a superposition, but today we're making measurements, which in quantum theory, once you make a measurement, the system becomes in that state. So for example, if you have an electron, which might have a spin up or down, it can be in a superposition. But if I measure it now and find that it's up, from now this point forward, it's up until it interacts with something else that could change it. So in the same way, Stephen was saying that as we make measurements on the universe today, we are defining the universe today. In the same way that I'm defining the electron, which is can be up or down, it's either up or down when I make the measurement. That's what's happening as we make our measurements today. So in that sense, we are defining what the universe is through our measurements.
Mm-hmm. So the result of both of those, the no boundary proposal and the quantum universe, has been integrated into a core concept to deal with the ultimate kinds of questions: how to understand the world, where did it all come from, and ultimately, did the universe, did all reality need a creator? And Hawking said famously, traditionally, these are questions of philosophy, but philosophy is dead. So by saying philosophy is dead, the criticism is, of course, is that Stephen, with that statement, was in fact doing philosophy, but it was amateurish philosophy or bad philosophy.
Yeah, so when we wrote the grand design, we talked about the implications of this no top-down cosmology and the no boundary proposal. And one of the implications was that the universe started in many different guises, and that the universe at the very beginning, or if you go back in time, you will have in existence parallel universes all with different physical laws. So the physical laws could be anything. And it's over time that a lot of those universes died away. Other ones are still going, and we are in one of them. And we happen to be in one that allows life, because otherwise there'd be no one there to do the measurements. And in that theory, you see that the universe actually could have come from nothing. There are many universes, and it could have come from nothing, so you don't really need a creator. So in the brief history of time, Stephen talked about the need, whether or not you need a creator. And we took that further in the grand design, because we showed that not only that the universe not only did you not need a creator to determine the laws of the universe, but even that the universe exists. So one day I'm sitting in Cambridge working with Stephen, and I'm still haven't left my room yet in the university, and I get an email from him, and he has in the email, he says, oh, I want to change some of the stuff, and I guess it was the introduction of the first chapter, blah 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 blah, and then comes a sentence, and so while philosophy was once useful as a way of understanding the world, we don't need it anymore because philosophy is dead, or something like whatever you just said. That was the sentence. And I'm going, Stephen had told me that one of his goals in this book was to create a new philosophy for physics, because we're talking about parallel universes. So what's the questions? What exists? What doesn't exist? What does it mean if something is in a parallel universe, but we can't get to it? What does it mean if we can never in principle observe it? So is it real? And there's a lot of interesting questions that come up. And he wanted to talk about those questions, in my view, not as a professional philosopher, but as a physicist who has every right of saying, here's the way I look at my work. Now he's saying he wants to say philosophy is dead. So I go to the office and I talk to him about it, and I'm going, well, and this shows you typically how we would work, because as I said, we would get things back and forth. So we start to have this big debate, and I say to Stephen, well, this line, philosophy is dead, is going to upset people. And he goes, I said, it's not really accurate. And I actually brought a philosophy a textbook with me that was, because we were talking about such issues at the time. It was a philosophy textbook on the nature of reality. And I had all these passages marked so you could see what people had said previously. He didn't want to look at it. And then I said, well, what would be accurate would be to say, philosophy is still useful for ethics, philosophy of life, the philosophy of different subjects. There's a philosophy of science. There's a philosophy that you use in linguistics. So that other than these other uses of philosophy, but for understanding the laws of nature, philosophy is dead, because I totally agree with and think I can defend that. Philosophy has never built a rocket ship or an airplane, doesn't understand what a laser is, can't tell you why the Earth orbits the sun, but physics can, but philosophy can answer other questions. So I wanted to say something like that. So I explained that to him, and he's typing out. I, look on the screen, circle around and look, and it says, he writes, but your sentence has no punch. So I argue a little more, and I'm waiting for his answer. And now he's switching himself to write something, but this time he doesn't write anything. He just makes the computer say what he just said. Your sentence has no punch. So I argue some more about it and go try to convince him. And this time, what he does is he turns up the volume to maximum, and it's yelling at me, your sentence has no punch. And I finally, all right, okay, all right. And then I said, all right, well, okay. Hopefully from the context, people know what we mean. So let's go ahead and do it. And of course, it was the one sentence that a lot of people pick out to attack us. And they're totally right. Neither of us is a professional philosopher, definitely amateurs. And that sentence taken out of context is maybe wrong. But in the context, I think you'll see that it meant what I was trying to say. And anyway, that's the story.
Taking it further, a lot of conversation deals with Stephen's approach to a creator and to God. His comment about what breathed fire into the equations has been used by theists to suggest that Stephen had some supernatural sense that something had to happen. And then, of course, many people use Stephen's no boundary in quantum universe to show that there's no need for a creator. In fact, use that to defend atheistic positions. Yet Stephen, I think you said in the book that he did not want to be considered as a typical atheist or even a deist. Describe his approach to that.
Well, he was 100% atheist, but he didn't want to be a public atheist or public intellectual atheist. First of all, he didn't want to insult people. We talked once about Richard Dawkins' book, The God
Delusion.
Delusion. It was a dilemma. No, not the God delusion. And he knew Dawkins, and he said he did not want to be like that. He didn't want to attack people, insult people, make them feel bad about their beliefs. And in fact, if you look at his relationships, Jane, his first wife, Elaine, the second wife, and then Diana at the end, they were all very devout theists, and he would go to church with them. So he had nothing against it. It's just that he also, to be intellectually honest, he followed the physics where it led. So if the physics says there is no beginning or you don't need a creator, then he wanted to say that. He did not want to attack God. He wanted to, in a positive way, say what it was that science said. And he was very much against people who believed in miracles. He felt that the whole history of science is an argument against miracles, that never once in a laboratory or any scientific observation has anything happened that was a miracle that didn't obey the laws. And he felt that, so he was passionate about that, about arguing that nature obeys the world obeys the laws of nature, but he did not want to criticize or alienate people who believed in God.
Yeah, Len, your book, again, was one of the best books I have read in recent times, certainly in COVID times. Stephen Hawking, Memoir of Friendship and Physics. I thought it was very balanced, very human. The physics was excellent. But yet there is, as you well know, been reviews of a book that talks about the selling of a scientific celebrity, which is basically criticizing the public persona of Stephen. And I just take this from one of the reviews. This is not from that book, but it was from a review of that book, that behind the image was a fair bit of bunkum. Do you agree with that?
I don't know what that means, but I didn't read. I know the book, and he interviewed me.
Basically nonsense, kind of a Barnum and Bailey presentation, kind of a phony persona to make money and sell books. as opposed to real substance?
Well, if you read my book, you'll see exactly what was there, what substance there was, and I mean, Stephen himself was the first one to laugh at how people treated him. So he didn't take it that personally, and I think he enjoyed his fame and being a spokesperson for science, and he agreed with people who thought that his image was exaggerated. He always said, would roll his eyes if someone compared him to Einstein. I talked to him about whether or not about his Nobel Prize possibilities, and he was clear that he didn't think he had those because his well, I won't get into it. Although now it looks like maybe if he had lived a few more years, he would have maybe got it with Penrose. But Stephen had a very clear-eyed view of it, and a lot of this. But it was a very big marketing machine. He did need money for his medical care, which is quite expensive, and he did write the books partly because he needed that money. I mean, he was an evangelist for science, but he was also a person who needed to survive. He needed 24-hour care, and if he didn't have the money for it, he'd end up in a home somewhere, not in a room without the ability to read as he could. He had people turning pages. He would have had, his life would have been considerably worse, as it is in our society, if you don't have the money for when you're sick, for private care. So that was part of it. But I didn't see any, I didn't see any hokum or whatever that, but I see, it's kind of funny because that book, I think, is the title of the book is called Hawking Talking. But I haven't read the book, but it seems to me like this guy is trying to make money by saying that Hawking was just trying to make money. So I don't know. I'll probably do have to read it sometime or look at it. But just for fun. But I think that, as I said, so that there was something. I mean, his persona was exaggerated, and he laughed at it, and he also took advantage of it and enjoyed it. But he was never one, I would say, who did anything disingenuous or dishonest about it. And never did he promote himself as more than he really was. And in the physics world, everyone had a very clear idea of who he was. And he was a very influential, important figure, but not the leading physicist of his time or of the century or another Newton or so forth.
Let's pivot to some questions. Our audience has been sending lots of interesting questions. We only have time for a few. Maybe I can just characterize them into different categories. I'd say about half of them are pure physics questions, many of which I think you've answered, at least in general terms. And many of them are meaning or God kinds of questions. Let's start there. And in the questions are in a bigger sense. For example, one person, I'll give his name, is Victor, says that if there are no minds around that experience the conscious experience of the universe, would then the universe be the equivalent of nothing? In other words, it's an attempt to show that consciousness is critical for reality to exist.
Yeah, that's not that was not Stephen's belief, and it's not my belief. And I think very few physicists believe that, but some people believe that. The original formulation of quantum theory relied somewhat on that. It was a little bit, what's called the Copenhagen formulation from the 1930s, a little bit vague. But here's the thing with quantum theory, that the interpretation of what's going on, which is where you would ask these questions, is separate from the application of it. So whatever you think is going on, whether you think things are changing due to consciousness or for some other reasons, or let's say the Everett viewpoint that the universe is constantly splitting into other parallel universes, whatever you want to take, that has nothing to do with the answers that you get when you do the calculation. So fortunately, quantum theory is a theory, a mathematical structure where you can look at a situation, make predictions, verify them, and you're fine. Now, what is it that you're really doing? Physicists still haven't solved that problem. Stephen believed in what's called, you can look it up, the many worlds interpretation, the Everett interpretation. I won't get into it here. That was what he and most cosmologists, I think, believe in.
Hmm.
But I don't even know of any physicist who believes that you actually need consciousness.
There's always the debate of realism and anti-realism. What we're doing, you have a term that I think would be a good response to many of the questions that we're getting, what you call model-dependent realism. So when you use the combined phrase model-dependent realism, how does that differ from realism?
So the question, and this is what we were talking about that day when we said philosophy is dead. We were two amateurs talking about philosophy. Realism, the question is, when you observe the world, what is behind that? So one way of looking at it is to say, well, all I know is I have sensory input and my brain is organizing that into some story. And I don't know anything beyond that. That my retina is firing and my ears and my brain's processing it. And I don't even know if I don't even know if you exist, Robert. I can't know anything beyond my senses. And the job of my brain and of science is to explain to myself what these senses is bringing me. And I can't say anything beyond that. If you're a realist, you think, no, there's something out there, has nothing to do with me. And my senses are perceiving something that's there. Okay, now this is not a scientific question because it has no implications to a measurement or to any predictions. It's just a way of interpreting things. And Stephen was in between, and that's why we call it model-dependent realism. He felt, well, he feels like that he's not going to say there's nothing out there, but he believes that there are different alternative, equally valid realities. And we talk about it a little bit in the book, but if you read the book, you should look at the part about the fish bowl with the curved bowl and how the fish.
I didn't think we got enough time for that. Please explain that. I'm going to take another couple of minutes, and I love that story. So please.
Okay, so Stephen looked at physics and said, look, there are different formulations of quantum theory, like Feynman's histories, multiple histories, or the original with wave functions that describe the world in totally different terms of totally different concepts and different things going on. If you look at animals, probably a bat's understanding of the world is totally different from ours. Yet we in the bat will avoid, let's say, running into a car, or both versions of quantum theory will give the same answer. So he's saying there's different ways of looking at the world that can be equally good. So then we get this metaphor about the fish scientist. So there's a fish scientist, whole civilization of fish that live in a curved bowl, okay? And the fish are, when they look outside, they can see that there's a difference between their universe that they can be in, but at some point something stops them. We know from the outside that it's a bowl, but look at the fish's point of view. They don't know what it is. They can't step outside. So they just know that at some point there's this force field that stops them. And they can see things moving on the outside, just like they can see things moving on the inside. And on the inside, they see that stuff moves in a straight line, Newton's laws, right? If you start swimming and you stop, you just keep going for a while, okay? And but the stuff they see outside moves in these weird curved paths, because we know from the outside, and we've done some physics, that when light moves from air to water, it bends. And the effect of this bending with the curved bowl is that if you're inside the water and you look outside, there's distortion. If you've all seen that at some point. So the fish think there's a separate laws of the universe for the outside than there are for the inside, and that works just fine. They make whatever predictions they want to make. If I happen to be outside, I throw a pencil and the fish is inside, he sees it curving, he can calculate how it's going to curve because he knows those laws. I would say he's incorporating the laws of optics, but he doesn't know that. He just knows that on the outside things curve. Then some brilliant Einstein fish comes along one day and goes, no, I've figured it out. The laws outside are the same as the laws inside. Everything moves in a straight line. Things only appear to curve because when light from those things go into our universe through the bowl, that distortion makes them seem like they curve. And so you start getting this whole argument between the fish that like the old way and the fish that like the new way. Both ways, they can predict what happens when I throw on the outside the pencil, right? The question is, now imagine you're in the fish universe. And I mean, you have to really be serious about this. You cannot step outside. Don't think about me looking at it. Don't think about all your prior knowledge as a human of what's really happening. Think about it as a fish. They can't get out of the bowl. They can't tell that there's air out there, what's going on. They can't do either one. They just know that they have these two theories that describe things in different ways, and they're both right. They're both right in the sense that they make the same predictions. They just disagree with what's really there. That's model-dependent realism. Stephen says, accept that. That is our situation in the world. That is the human situation. We can never know the real versus the unreal. We have to be able to accept different but equally valid versions of reality. So that's model-dependent realism.
I want to ask you an unfair question. From Stephen's point of view, and then from your point of view, on a scale of 1 to 10, what is the confidence level that the no boundary proposal of the universe is real? 1 to 10 for Stephen.
Well, what do you mean? So by you mean valid?
Just start with a number. Give me your number.
But do you mean? But I want to know what you mean by real. Again, we've just talked about how real is a little bit. Do you mean valid when you say that? Because there are people who don't believe it.
Okay, I mean representing reality.
Well, the first question is, was he right? Okay, I should answer that first, and I would say that he would probably say there was a 90% chance that he was right. That was the work of all his work that he was the most proud of.
Okay.
I think in the cosmology community, it'd be more like 50-50.
Okay. How about you? How about you?
I'd say 50-50.
Okay. Okay.
And
then how about the quantum universe where the
top down?
The top down, yeah. The present has an impact on what.
Well, I think the ideas are correct. Also, the ideas in the no boundary proposal, the ideas are correct. But remember, he couldn't do the math, so he's making a lot of arguments based on math that you can't do, and you're assuming this and that. And so I would say for that reason, it's probably also the same, about 50-50. Okay. And cosmology today it has many different theories, and it's a very unsettled field. So anyway, if it's true, is it real? Well, in the sense of Stephen, in the model-dependent realism sense, yes, it's real. It's true. You can think about that way. It gives the right predictions. You're perfectly valid in thinking about that as being real. And if someone else has a different way that gives the same predictions, that's real too.
Good. Well, Len, this has been terrific. I've enjoyed it. I loved your book, Stephen Hawking: A Memoir of Friendship and Physics. It was really a delightful read, very well written, and I felt that I spent those 5 years with you. I felt like I now know Stephen, and many of the characters. Kip Thorne, of course, has been on Closer to Truth, as you have. Jim Hartle has been on Closer to Truth, so people can look up Jim Hartle and hear him explain the no boundary position on closertotruth.com. And it's been great. I really enjoyed it. And look, when your new books come out, you have a standing invitation to come back, and we will talk about those with the same energy and enthusiasm. So to all of our members, I hope you've enjoyed today's discussion. Everyone can purchase Len's book, Stephen Hawking: A Memoir of Friendship and Physics. See it at his website, leonardmlodinow.com. And we'll be doing more events like this often and soon. We're getting great feedback. We appreciate the members, and just pay attention to your emails when you see future announcements. And if you think that friends or colleagues would enjoy this discussion and discussions like this, send them to closertotruth.com to register for their free members account as well. So we look forward to seeing you on more Closer to Truth Live and Closer to Truth chats. Thanks for being with us.
Okay. Good. And